record again. All right, so it's been a while since we met. I wanted to go back to this picture. So I changed this to look at the cumulative rather than the distribution function for a binomial. And I'm wondering if that helps make things clearer. If you recall, at the end of the last lecture, we were discussing how you create sample complexity bounds in an elemental fashion. And the claim was that if we're looking at 0-1 loss, then we get a binomial distribution with a mean equal to the expected error rate of a classifier. And then I showed you a picture where instead of having a cumulative, I had just the distribution function itself. Is this picture here clear? So the idea now is that this is the cumulative of the thing that I showed last lecture. Yeah, we don't hear them. Why don't we hear them? Oh, now we hear them.
Oh yeah, we need to mute this one.
Yes. So I guess I wanted to ask two questions. One of them is, are there any questions about the sample complexity bounds? And is this a bit of a clearer picture? So the idea is that the green is the number of heads that you observe, the number of errors that you observe for your classifier, and then the red is what a direct inversion of the binomial tail suggests as a bound, and then the blue is the bound that you get if you use the square root form of the Chernoff bound. Everybody's bored? Okay. No questions? All right, I will assume forevermore that you don't understand everything perfectly. Hopefully that works out. All right. So I want to get to discussions about exploration and whatnot, but I felt like I needed to have at least one lecture and maybe two on optimization and online learning. Because there's a lot of details about how you optimize, which matter quite a bit in whether or not you succeed in actually doing optimization. So I'm going to be using VW, which you can download here if you want and compile it yourself. And I'll be using this data set, this RCB1 data set, if you're interested in it. Are there any general questions right now? Okay. Okay, so I'm going to just focus today on linear learning because I think that's kind of a building block for doing more complex things. So when I say linear learning, I mean not precisely linear. I mean kind of linked linear. So what I mean is you have some features. That's the vector x. You have a label. And when you're doing regression, you're just trying to predict that label as a scalar value. Then you want to learn some weight vector, which has the same dimensionality as the feature vector. And you want to find that weight vector, which makes the dot product of the weights and the features be close to the actual label y. All right, and then if you're thinking about classification, well, then y is just going to be plus or minus 1, and you add a sign to things. You try to minimize the error rate. So this should be pretty routine so far. Now we're going to think about online learning. So in online learning, what happens is you're kind of intentionally operating one example at a time. And that's kind of more difficult as an algorithm, but it has some significant advantages, which I think has made it actually fairly dominant as an optimization approach, and it makes applications to true online settings fairly viable. So in an online setting, what happens is you start with your weights all 0, and then you repeatedly observe features, you make some prediction, and then you observe a label, and then you update your weights. Right? So, and the primary thing is here is step 4, because the prediction is just always a dot product. And step 4 is what varies from algorithm to algorithm. Okay, so sometimes you do logistic regression, and then what happens is you essentially have this link function, which has a totally different form. It's a monotonic transformation of the existing dot product. There's other times you have other link functions. Those are just monotonic transformations. When I say linear learning, I mean linear with any kind of link function, because the complexity of doing all of these is about the same. And the ways that you do all of these is about the same. All right, so so one example to keep in mind is what the update rule looks like if you're just doing gradient descent on squared loss. So if you're doing gradient descent on squared loss, then you have some learning rate, that's eta, and then if your prediction is equal to the truth, you do no update. And if your prediction is far from the truth, you have a big update. And otherwise, you proceed. Okay, so I'm going to show you an example. This is so there's a data set here, which is used for document classification. It's the Reuters. It's actually a fairly old data set at this point. There's about 781,000 examples. There's about 60 million non-zero features. It's about 1 gigabyte in size. And the format is kind of label and sparse features, which looks like this. So let me show you here. Text. Right. So you can see a label here. This is essentially the same as the SVM Lite format, which Thorsten at Cornell invented a long time ago, except there's a bar to separate the label part from the feature part. And then you just have sparse features. Right? So feature 13 has value of 3.96 times 10 to the minus 2. Feature 24 has value of 3.47 times 10 to the minus 2, and so forth. Right?
Is that TF-IDF feature?
Yeah, these are TF-IDF features. All right, so let's do word count on this. So it's 781,000 examples. And then we can do size. Let's do it with it's 1.1 gigabytes. So this is a fair size data set. And now we want to try to learn with this. So we can say, oh, I want to do stochastic gradient descent with this data set. And we can run along. And what we observe is that after about 1.7 seconds, we have a predictor. It's doing something non-trivial. This is reporting squared loss. If we wanted to report binary loss, we'd do S binary. You see that the error rate is getting down. It's down to about 5.9% in that pass. So what this class is really about is telling you what's going on here and how to improve what's going on. So 5.9% it's kind of a reasonable number, but if you have a better learning algorithm, you can get down to like 5.15% or something like that. And the time can be about the same. Okay, so this is vanilla. Let me check something. So when I say gradient descent, does everybody know what I'm talking about? Yeah. Does anybody not know what I'm talking about? There we go. Okay. Okay, so I was trying to come up with a title for this lecture, and I was thinking a good title is "What is Wrong with Gradient Descent?" Because this is vanilla stochastic gradient descent on squared loss. There's some things you can do to tune learning rates and whatnot, but no matter what you do, you're not going to get very good performance compared to the best you can do on this data set, at least not in a single pass.
So it's like without a patch.
What's that?
It's an online fashion, so there's no patch.
Yeah, so this is running in an online fashion. I'm going to kind of show you a little bit about what's going on. So we're running through, we print out on an exponential backoff each line. We print the average loss. So what we're doing is we're evaluating the loss one ahead of where we're training, which means the loss kind of deviates like a test set. This is the average loss since the beginning. This is the average loss since the last printout. This is the current label. This is the current prediction. So you can see that we're getting pretty close to making good predictions. And this is the number of features for that example, the number of non-zero features.
Was the training data shuffled in any way? Because many of the data are, if there is some kind of correlation.
Yeah, so when you're doing online learning, there's an additional failure mode that can happen compared to batch learning. Additional failure mode is if you take and you put all of the label 1 examples before all the label -1 examples, you're going to be very unhappy with the solution that you get. It'll appear very good because the constant feature is very powerful in predicting the label most of the way through, but it doesn't work very well. So yes, this data set was permuted but when it was created. Yeah, Eugene, right?
So yeah, so if I have a control over the data set, can I and I'm an adversary, so can I break this system by like supplying the wrong results, like for some time, and then it will change because it doesn't look back, right? So it updates the weights based on just the previous result of y. So if I supply some of data that is wrongly classified, that I've wrongly classified, can I break the classifier?
So it depends a little bit on what you mean by break. So you can certainly, if you change a lot of the labels, you can make the classifier predict the wrong thing with respect to the unchanged labels, but that's kind of inevitable if you're changing the labels, right? So when people do the analysis for these algorithms, what they do is they say, I have a set of different predictors, and I would like to compete with that set on the labels that are supplied. So if the labels that are supplied are bad, then will compete with the bad set of labels. But that doesn't give you any strong guarantees about what happens to uncorrupted labels.
What is this example weight called?
Oh, yeah, so that's actually fairly important. There's a number of times when the learning algorithm here can take into account an example weight. So you can say, this example is twice as important as that example, right? Now, here all the weights are implicitly 1, so, it's not really doing anything useful, but there's a lot of situations where by manipulation of the example weight, you can express the problem that you want to solve much more directly than otherwise.
So the example weight is like the sum of all the example weights still.
Yeah. Other questions?
Does it make sense to set the example weights in such a way that, like in an epoch, like you just increase the weights of those examples which are wrongly classified? So like
a boosting style?
Something like that. I mean,
yeah, so boosting is an example where you manipulate example weights. I'm kind of 2 minds here. In many situations, misclassified examples are outliers, and you should get them wrong. And so increasing their weight can be a little bit problematic, right? So let me go this another way. So when you're doing active learning, it's often you exclude examples from labeling, right? Because you decide that the learning algorithm decides it doesn't need those examples. And then often it will end up excluding outliers because they're far away from the boundary or something like that. And your performance can actually improve when you do that. I've seen a number of cases where that happens. So boosting, I think, can be useful, but I think boosting is mostly it's most useful when the data is clean. Particularly if you're using the exponential loss like AdaBoost. If you use the more gradient boost-like approaches, then I think you can tolerate a bit more noise. Okay, so this corresponds, right, so these TF-IDEA features correspond to various non-stop words in the documents. The category is essentially CCAT or not, which means essentially a business article or not. And it trains in like a second or two on my laptop. Okay, so what do you get from this? Well, what you can see is it's very fast, right? It runs through the data very quickly. I guess I've met a number of senior machine learning people who are not used to online learning, and then these kinds of speeds can be rather dramatic for them. I remember when VW first came out, I was working with this example, and I went to a workshop, and there was some guy from Stanford, I think, who was talking about using MapReduce to parallelize support vector machines on the adult data set, which is smaller than this. And he's saying, look, I got linear speed up and over all my cores. And then, I showed this example. And this is like a single machine laptop, not a big beefy server. And it's just crushing things. So the speed here is excellent. But the performance is not so excellent. And the rest of the class is going to talk about, to a large extent, about how to get the best performance possible out of an online approach. And I think this is very relevant for, so there's sort of two kinds of online. There's online learning where you're actually in an online environment and you're just seeing examples come at you. You need to respond to them in an effective fashion. That's actually relatively rare today. We will be discussing that later, but that is relatively rare. Much more common is online optimization, where you're running through a data set and you just don't load it all into memory. You're just working through it one at a time, trying to tweak things. So this online optimization approach is what's used to train all kinds of deep neural fun stuff. And so a lot of these tricks that I'm talking about here actually do apply in an online optimization setting.
What would you call mini batch as like online learning?
Mini batch is online, yeah. I mean, as long as the mini is very small compared to the full batch, right? All right, so why do you want to do online learning? Okay, so you get fast convergence. That's really nice. It's very RAM efficient. So when I run VW, it doesn't load all the data into memory, and that means that I'm not limited by memory in terms of the amount of data I can have. The first limit that comes into play is the model size in memory. Okay, so there's this cool fact that online learning is the same as online optimization, and that means that you can study how to do online optimization, which is very practical and useful right now, and actually learn something about how to do online learning, which is very cool and maybe the thing to do tomorrow, or maybe today. And then the last thing is that there's some situations where online learning is absolutely essential. So if you have a problem where the nature of what you're trying to predict is changing over time, then you need to be doing some kind of online learning, or simulated online learning at least, in order to effectively address it. Okay, so let's go into a bit more detail about updates. Typically what happens is you define some loss function, which takes as input the prediction and the true label. And then you update according to the negative gradient, where 8 is some learning rate. And then most of the tricks are in the choice of the learning rate. Okay, so here's a bunch of examples. Probably you guys have seen graphs like this in the past, but it's worth kind of going through things. So the purple is the 0-1 loss. The yellow is a hinge loss, like a support vector machine. The blue is a logistic loss. And then the green is a squared loss. So VW defaults to the squared loss, but there's other things which are available.
This is the training or the on validation?
Well, there's a question about what you optimize and what you report. And those are kind of different things in general. So if I add the message binary, it reports the 0-1 loss in this column over here. But if I take that away, it just reports the loss which is optimized. And now the question about whether or not it's a training loss or a test loss, let's defer for a minute. Okay, so I've written all these losses in such a way that you can see that they can form an upper bound on the 0-1 loss. So that's helpful. One question which comes up is, which loss function do you want to use? And I think if you care about, okay, so it depends, is I think the real answer. So let's think a little bit about which loss function you want to use. So there's a bunch of questions you can try to answer with data. Back when I was trying to buy a house, I was trying to figure out what a typical price for a house was. What is the expected return on a stock? What is the probability to click on an ad? Is the digit a 1? And so forth. So for the first question, what is the typical price of a house? Which loss function would you want to use? Squared loss? Okay. Anybody else?
Quantile loss.
What's that?
Quantile loss.
Quantile loss. Why?
Because you want to know what's relevant to you, not what's overweighted by other rich people buying billion-dollar homes.
Yeah. Okay, so what about the expected return on the stock? What would you want to use? What would you want to use for expected return on the stock? You're investing your money with a learning algorithm. You know, it's fairly important you choose the right loss function because otherwise you lose all your money. Which loss function do you choose? Squared loss, okay. Why?
Safe.
It's safe. Nobody will blame you if you choose squared loss. Okay, what is the probability to click on an ad? What would you choose?
Binary. Binary.
What is binary loss? 0-1 loss, you mean?
Yeah, 0-1.
So one thing which is a little bit tricky here is that optimizing 0-1 loss directly is actually very difficult. So typically you want a loss function where you can actually compute a derivative.
I mean, how about log probability?
Yeah.
Log probability, yeah. Just something like logistic. Yeah. Is the digit a 1? What would the loss function be? So you have a bunch of digits. You want to know if is the digit a 1 or not.
0-1 loss.
0-1 loss, yeah. But you need to translate that somehow because you typically don't optimize 0-1 loss directly.
Yeah.
Okay, so these are my answers. So I went with quantile. And the key thing to understand about the quantile is that the minimizer of the quantile is the median. Right? So it's a little bit helpful compared to squared loss because there are some prices. If you go and look on Zillow, you'll see there's some prices that are just very aberrant. Maybe you're selling your house to your kid for $3, right? Or maybe there's some super rich guy that's selling a house nearby. Now, granted, this is conditional, so we're trying to find the conditionally right value. So you might featureize things to take away the thing, but still, median is very good at getting at what's typical rather than the average, which may not be so typical. Expected return on a stock, I think squared loss is actually the right answer because you're really just trying to optimize the expected value. Okay, so if you could do squared loss for number 3, but I think typically people do not do that. And the reason why is because people don't click on ads very often. So the probability to click on an ad is almost always quite small. And that means that, right, so let's think about what is the difference between the squared loss of predicting 0 and 0.01 when the truth is 0.01. Not very big difference, it's quite small. So logistic loss is much better at getting at relatively small probabilities. Is it just a 1 is a classification problem? You might go with hinge loss there, and the reason why, if you look, is the hinge loss is kind of the closest approximation to 0-1 loss. But really, you could leave it up to empirical validation. So it turns out that every one of these loss functions we've talked about is kind of proper for the purpose of classification. Since that if you can optimize this loss up to what you call a base classifier, I guess, then you will get an optimal 0-1 classifier. Right, and then I think another thing which is always very important to keep distinct in your head is what are you optimizing, and how does it compare to what you actually care about. So often it's some version of 0-1 loss, but there can be many variations about what loss function you care about. Okay, so I wanted to go through one proof. So I'm going to show you a proof that the optimum for quantile regression is the median. Okay, so let's just think about this in, let's think about, suppose that the distribution over y given x is this strange thing. Okay, so that's some distribution. And now let's just think about 2 tails which have the same mass. These actually do have the same mass. Okay, so what are the possible values? What are the possible y hats on the x-axis which minimize the absolute value loss? So when I say absolute value loss, I mean your loss is the magnitude of y hat minus y. So your observations are drawn randomly from this distribution. But let's just suppose the distribution is limited to these parts here for now. So you have a random observation from here or here. And now the question is, where is the y hat which minimizes your expected loss?
Somewhere closer to 0.5, between 0 and 0.5.
Between 0 and 0.5. Why do you say between that? Remind me, what's your name? Remind me, what's your name?
Oh, Aman.
Aman?
Yeah. because 0.5 has higher mass, like just at that. That's like decreasing, so you want to keep it closer, prediction.
Okay. Which question?
So I'm saying, since the mass is equal, isn't anywhere between -half and half the same?
That's right.
Any label, so it doesn't matter where we pick it.
Yeah. That's right. So it's anywhere between -0.5 and 0.5. Sorry, what was your name again? I'm still learning names.
Roundton?
Say again?
Roundton?
Ronton. Okay.
Yeah.
Cool. Right. So how do you see this? Well, let's suppose that we pick 0 just as a possible value, right? Then the expected loss contribution from the left part is going to be some sort of expectation of the y value, expectation of the magnitude of the y value, because it's just going to be y minus 0 magnitude, right? If you're taking the expectation of a value, you can replace that with its mean. And so you can think of a point mass on the left and a point mass on the right. And then because these two masses are the same, it doesn't matter where you are as long as you're in between. Okay, so does it work for any tails? It means it actually works for the tails. So these were tails which had a mass of 1/4 and 1/4. You can make them have a mass of 1/2 and 1/2, and that's essentially why the minimizer of the absolute value is the median. Okay, so now let's discuss success. In traditional batch-oriented learning, we're getting to your question now. What you do is you have a train and a test set. That's kind of inconvenient when you're doing online learning. And so it's helpful to look at progressive validation. And the idea with progressive validation is that on time step t, you first make a prediction, and then you evaluate your loss, and then you take the empirical average of those losses. And so we're going to, if we go back to the online learning setting, right? We make a prediction, and then we find our label. So the prediction is defined before we know what our label is, and so the label is not contaminating the prediction in any way. Okay, so you can prove various things about this. We're doing progressive validation. So you can say, look, suppose you have any distribution over x and y. And let's suppose that we have some expected loss at time step t with the weights that we have at time step t. Okay, so then we have our empirical average loss, L. We have our expected sequence of expected losses, which we've taken expectation over. So this is also something in the same range as the losses. And claims that these deviate from each other by something like square root of log 2 over delta divided by 2t.
T is the size of the validation.
T is the number. There's no validation set here. We're just testing one ahead of where we're training.
Oh, I see.
Right. So it's not a validation set. It's a progressive validation process. And so this is a different experimental protocol than would typically be used or necessarily be used for a batch learning system. And the justification for the experimental protocol is essentially a theorem like this. It says that we deviate like something like square root of 1 over t.
So what's K again?
T is the number of samples that we're testing with.
Testing with one.
What's that?
But you said testing.
We're going to test with a sequence. So we test in timestep 1,
Oh, so
and then in timestep 2, and then in timestep 3, 4, 5, 6, and so forth.
So capital T is same as small t?
Capital T is the total number of samples that you test on.
And what is small t as a random variable? Like what is
Small
what
t
the
is the time step.
expectation?
Small t is the time step.
Expectation for
Yeah, so it's a time step you take the expectation over. So little t is the dummy variable.
So that's that's similar to the printouts on VW you showed.
Yes.
Basically for
So that's exactly what's happening here. So these are progressive validation numbers here and here.
But for every time you're doing validation on a larger T, because you didn't everything that you did that came from since the last printout.
So this line here is from the last printout. This line here is from the beginning.
Okay, so the 0.17 is on 262.
Yeah, 262,144 examples.
Okay.
And then the deviations are going to be bounded by something like 1 over a square root of 262,144.
Mhm.
Right? So if you recall from the lecture last time, this kind of sample complexity bound is exactly what you get with a train test type of approach. And in general, they're not actually precisely the same because there's a martingale process going on here rather than a simple binomial, but they're pretty close. Okay, so now what does this mean? It's a little bit tricky to understand it. One thing this does not mean is that the last set of weights you have is good, right? Because it might be that the last set of weights is crazy for some reason, and then you have a bad prediction, and that's just kind of rough. Even though the average was good throughout. So this is really a way of measuring the quality of the algorithm, the learning algorithm, at least as much as it is the quality of the solution. If you want to be guaranteed to get a good predictor out of your learning algorithm, you really need to be drawing, and then you need kind of a two-step process where you first achieve something with a small progressive validation loss, and then you pick one of those time steps, little t, at random. So this is known as an online to batch conversion.
So this YT, we compute the loss at time t is the same as what we learned from it. It's the same example, right?
Yes, but again, we're learning after we compute the loss.
Yeah.
Right.
Where do you have a delta on the left-hand side? We should have a delta on the left-hand side, right? Or
No,
we
it's
don't?
in the definition here, like probability.
Yeah,
It's in
right.
higher.
Yes.
Okay, so we have deviations here, which are like a test set. And so we can trust these numbers like we trust some validation set or some test set. There is actually some advantage over using a trained test because, okay, so consider this number here. If your test set was the last 262,144 examples, your performance would probably be somewhat worse than this because about half of the test set is effectively used as a training set when you draw a random time step t. Right? Because it's as if you're testing, it's as if you're training on your test set. at least training. Okay, so let's imagine we have a train set, and then we have a test set. So normally we would just test on our test set. But instead what we could do is we could test on the first example and then train on it. Test on the next one, train on it, test on the next, train on it, test on the next, train on it, and so forth, marching through things. So that additional training that we're doing can give us better performance. So it's kind of cool. Usually that isn't too important. Usually the test sets are not very large compared to the training sets, so this is not a big deal. But the fact that you're getting a little bit of extra edge is kind of cool.
So procedurally, to get the prediction before every time you do an update, you retain the classification.
Yes. Yeah. Right. So let me try different loss functions. So you can do loss function hinge, I think. Okay, and we're reporting. Oh no, we need to. You have to say this is binary so that you always see the same reported loss. So we'll look at 0, 1 loss. So hinge is 59539. Doesn't matter very much. We could also do logistic. Okay, logistic was somewhat worse. You can test out different loss functions in this way.
Why was it worse? Why do you think?
So when you go and you look at what does logistic look like? So logistic is kind of funny because it doesn't go to 0 at 1. So it keeps going out. And so what that means is that the prediction of the dot product, the value of the dot product for these other loss functions, there's never any reason for the magnitude to be greater than 1 or -1. But for hinge, the value of the dot product could potentially be substantially larger. And the learning process tries to drive it to be something very large. So there's some limiters in the system which limit it to like 50, I think, because e to the 50 is already a pretty large or small number. But what that means fundamentally is that the learning rate for hinge for logistic loss is often a bit different from what it should be for the others. So that's probably the primary issue. Probably we haven't tuned the learning rate for logistic loss. But it may also be that there's just a little bit more difficult optimization.
But we're looking at the classification error, right?
Yes, that's right. So we're looking at the induced classification error when you optimize that loss function.
The loss can be not 0, but the classification error, but that doesn't explain the classification error.
Yes, sir. So inside of EW, this is something I haven't described in great detail, but when you make a prediction, that prediction is going to be clipped to the kind of a valid range of possibilities. So for things like squared loss or hinge loss, that'll be plus or minus 1. And that kind of stabilizes the optimization a fair amount. But you cannot do the same clipping with logistic loss because the loss function itself just keeps driving you further away from 0, 1. So it's not quite as stable in optimization.
Is it because like the weights are being pushed towards infinity, like their magnitudes?
Yeah, so everything is perfectly predictable. Then the weight magnitudes would be plus or minus infinity.
Is it fair to say that, as you said before, actually, so it's like we want to use logistic function when we, like in the case of clicking the ad, is like very, very rare event, and the data set that you have is not like full of rare events, right?
Right.
That's why the logistic doesn't work this way here.
Yeah. So in this particular data set, plus and minus 1 are about 50%. So you can actually see that, I think. So let's look at, let's just get rid of the logistic.
So in some sense, we favor one result over the 0 result here using the logistic. That's why we get such a high rate of error.
So -1 is only slightly more common than +1 in this data set. Because the best constant, so the best constant prediction for squared loss is -0.05.
I mean, it sounds somewhat like the saturation problem that neural network people talk about. Like when you use sigmoid and like, so there are those zones, these asymptotes where the gradient just becomes smaller. So if you are in those domains, I mean, you have to increase the value further, and it's more like a.
Well, again, we're not reporting logistic loss. We're just reporting 0-1 loss.
Yeah, but if you reached in that region, then it's very hard to move around.
So if you're in that region, then the learning algorithm has become relatively certain about its prediction. And that means that whenever it's predicting something there, it's actually essentially always correct. Otherwise, it would shift back rapidly towards the near 0 region. So that's fine as far as 0-1 loss is concerned. So it's really more, I expect it's more about the stability of the optimization and the choice of learning rate. There's certainly no advantage of logistic loss over squared loss in this setting because it's almost 50-50 between the two. Oh, and that, right, I could do quantile. I'll skip it. Okay, so yeah, so the cool thing about this is that I mean, I don't have to worry about a separate training and test set necessarily. I can just kind of rip through things, trying different options, and it's a little bit cleaner as a training discipline, as an experimental approach. Okay, so are there questions about the first part? Oof. Going down slow. Okay.
One thing which people do, maybe that you'll cover it later, it's like average weights with the learning. So like there was like there's some kind of perceptron training.
Yeah.
Something very similar. They just like average some D weights for stability. Is there a reason, or is it just a hack?
Well, there is a reason, but I'm not planning to talk about it in detail. So when you're averaging the weights, what can happen is these weights may be bopping all around because of the noise and the order of the examples that you observe, right? And so if you're averaging the weights, you're also keeping an average around. That average can get rid of that noise. So typically, almost always, that average will end up being good. The last average will end up being good.
Would be like maybe like the tail would have weights which are very similar, so the average would be close to the tail. It would be more like probably have less noise.
Yeah. Now, I don't actually do averaging in BW because my experience with it has been relatively poor, in the sense that I think averaging is often not harmful and sometimes helpful if you do it at the right time. If you start averaging from the beginning, that it actually ends up harming your performance. And now, what do? Well, you actually, I mean, it'd be another hyperparameter you'd have to tune in order to solve the problem. So, yeah.
So for subgradient optimization, you have to average. If you don't average, the last iterate doesn't converge. If you do subgradient optimization, maybe that's more than you want to talk about.
Yeah, so what I'm wondering is whether or not this is an essential lack of convergence or not.
An essential lack of convergence.
Yeah, so you can have a lack of convergence in the sense that your weights are not always the same value.
Right.
But this may not matter in terms of the overall loss that you observe.
Yes. I think in terms of the loss, it doesn't converge. With the gradient.
Do you have an example for that?
Not off the top of my head.
If you can find one, send it to
Yeah.
me. That'd be interesting.
Yeah.
Okay. Right. So let's go through how you modify SUD to do something a bit more useful, get better performance and so forth. Okay. So the first things you want to start dealing with is importance weights. So a simple example to think about for importance weights is spam versus non-spam. So it's generally worse to have non-spam in the spam folder than vice versa. So you would like to say that examples where an email is non-spam, it's more important to get correct than for examples where an email is spam. Right? And what should the ratio be? Well, back when I was working at Yahoo, I think it was somewhere between 10 to 1 and 20 to 1 would be typical ratios.
How do you quantify that?
It's not easy. You're trying to, you quantify that in terms of the importance weight.
Just like, how did you arrive at this 10 to 1?
Yeah, so how do you arrive at that is much more difficult. They weren't doing it in precisely the clean way that I'm talking about. They essentially allowed themselves some amount of misclassification of non-spam as spam rate. And then they, subject to that limit, they tried to optimize things. But a cleaner way to get at that is to manipulate the importance weights so that you obey that limit. I think this is about how you pose the problem. And I think often posing the problem is the most important part of things, since it's not so trivial to do. Okay, so now the question is, how do you modify the update rule to deal with an importance weight I?
Multiply by I.
Multiply by I, yes. It's the baseline approach. Okay, so you can use the baseline approach, and this is what can happen. So you're here, you're at the loss 1 when you predict 0 point, and then you update with an importance weight of 10, and you go over to something near loss 4. Because it overruns the prediction, basically, or it overruns the label. So that's not great. There's a different way to think about what an importance weight should be. You can say, oh, look, maybe if you have an importance weight of 10, then that should be 10 updates each with importance weight 1 in a row. And that's what so this repeated update is what happens when you do the 10 updates with importance weight 1 in a row. Okay, so that's that's good, but it's not very computationally efficient. This is another approach you can take, which goes a little bit further. You can say, well, I would like an update rule where you have 10 updates with importance weight 1. That should be equivalent to 20 updates with importance weight 0.5, or 40 updates with importance weight 1/4, and so forth. So you can say you can have a limit. You can ask, where do you end up in that limit? And it turns out that for all of the loss functions we talked about, you can compute what that limit is directly. And then you can just directly do that optimization. Okay, so there's some fun in how exactly you compute that limit, but that's probably more details than we should go into at the moment. So this is extremely helpful. So what happens when you have this kind of how far do you go approach, or limiting how far you go. Is things become much less sensitive to the learning rate itself. So you can get away with an extremely aggressive learning rate. So your learning rate could be 100 and something sane would happen. It may not be the best, but it would actually be something sane. So the default learning rate in VW is 0.5, which is very high compared to most implementations of SGD. A much more typical learning rate would be 10 to the minus 2 or 10 to the minus 3. But because we never actually overrun the prediction, the update doesn't do anything crazy, no matter what happens. So this is a bunch of different data sets playing around with different loss functions and different learning rates. And so we have every different setting of parameters is different dot. And what you can see is that it's almost always the case that the importance aware update just gives you better performance than the unaware update.
And what does this function S look like?
You're essentially doing some sort of integral to compute things, and it turns out that you can get that in closed form for all and the exact closed form depends upon the loss function. And so for hinge loss, it's very simple, right? So because there's no change in how far you update until you reach the hinge itself. And so it just says, go until you run out of importance weight, or you reach the hinge and then stop. Right, so let's go here. Say dash, oops, let's get rid of HT. Variant. All right, so we went down to 5.4% error rate. So it was 5.9, now it's 5.4. Okay. Next thing is adaptive learning. And this is very important, I think, for text-like problems. So in general, when you're doing learning, you want your learning rate to decay. And then the question is how. So typically when you're doing something like SGD, you're decaying like a 1 over a square root of t, or maybe a 1 over t. There's some variance in how you're doing that. But it's actually a bit better to have a learning rate which decays on a per feature basis. Right? So suppose you're running along and you see an example where you get the prediction wrong, and one of the features is new. You've never seen it before. Well, maybe that feature is very important, and maybe you should be updating that feature quite a bit. But maybe you don't want to update all the other features because those have been doing pretty well as far as your overall prediction so far. So what you can do is you can have a per feature learning rate. So the gradient for an individual feature is here. You're taking the gradient with respect to some particular dimension, I. You can add up the gradients squared for each individual dimension. And then you can use 1 over the square root of the sum of the gradients squared to decay the learning rate for that dimension. So this is called the autograd update rule. Who's heard of that before? A few people. Oh, a few. Okay. So this is adaptive gradients. This is a very helpful technique in general.
I mean, one thing is like, I mean, if your GIT at any point becomes very large, then that large value would always be in the denominator because there's something already, and your learning it will become very, very small.
That's right. So if your gradient is very large, well, if the sum of gradients squared is very large, then I guess the claim is that that feature has been shifted around a lot. And so maybe you don't want to shift it as much as you did in the past. Now, if you're trying to do nonlinear learning, I think this starts to break down because it can be the case that something shifts a lot and then it stays the same for a while, and then it shifts a lot It stays the same for a while, and it shifts a lot. And that's just what it needs to do in order to make good predictions.
Yeah.
But for linear learning, I think that's often this intuition is correct. So when you go to nonlinear, I think you want to think about modifications of this rule, which allow for non-stationarity and optimization to a greater extent.
Is that again derived for like linear setting?
It's derived for the linear setting, yes. So I would like to go through the proof, but I don't think we have time. There's a reference in the end which discusses it.
So another problem with Adaga is at the beginning you're going to amplify, especially if you have small updates, right? Because you're starting with your because you are dividing by potentially a very small number.
No, by the way, that summation should not be t or t minus 1. And if it's t, then the first update cancels. It becomes 1.
So,
One.
Yeah, so VW actually uses this. It uses t, not t minus 1.
The first update is always
Oh, I'm
1.
familiar with T as the 411.
Yeah, so, but when t equals 1, what happens is you just get this eta. The multiplier is 1.
Yeah, yeah.
So that's a reasonable default beginning place.
It means that the order is really important. Because, especially because you start amplifying in the beginning.
I don't know why you're calling it amplifying. Because this multiplier here, the GIT over the square root of the sum of GIT squared, is 1 or less.
Yes, but you can have a very, very small update, like 0.000001. So when you update, you're making it 1 in the first step, which means you're that's why I'm saying amplifying.
So we have a learning rate though.
Yeah, but relatively to how it would be in a purely online setting.
Relative to the other features.
No, not relative to how it would be in a purely online setting without the adaptive gradient.
No, you're amplifying it relative to the other features.
But every feature gets the same a minus.
No,
a.
yeah, but those feature gets it. So the others in the beginning are going to be more aggressive than the regular stochastic gradient descent.
I think
I think that's true. And then the thing that we just talked about, I think, helps with that quite a bit. And importance with invariant update.
Yeah, so had the interesting issues with this in the past.
like with t equals to 1.
Yeah, because it's like so especially when doing structural learning, in the beginning everything is very sensitive. If you're doing something stupid, and then later on you want that you downweight the features aggressively. You're doomed.
I think I'd have to see it. It's so one thing which is certainly true. Oh, there's a question over here.
Yeah. Sometimes we use exponentiated version of gradient descent rather than just plain version. Do we have adaptive rule for exponentiated gradient also?
I haven't seen an adaptive version of exponentiated gradient. It may be out there, but I haven't seen it. I used to actually have exponentiated gradient inside of VW, but I found that it was relatively sensitive as an update rule.
Yeah, I actually tried to use a bunch of AdaGrad and Ada stuff to apply for exponentiated gradient, but it actually makes the problem worse. So I just wonder whether there's recent progress for the adaptive rule for an expert-based line update.
Not that I know of.
Thanks.
Remind me, what's your name?
Moonte.
Say again?
Moonte.
Moonte. Okay. All right, so we can use SS adaptive to get this. And it ends up being a case that, yeah, it's not very good. It doesn't help very much by itself. Oops, let's go here. All right, so let's talk about one more thing. Let's talk about dimensional correction. So if GIT is a gradient for feature I at time step t, your update rule ends up looking like this. You have the weight, it's assigned the weight minus some constant times xi. It's kind of weird because though your prediction is W times Xi or Wi times Xi. So you would expect, so if you double the features, then the weight needs to have to give you the same prediction, right? But that means that if you have an Xi here, which is like 100 or 1,000 or something very large, you know, the weights are going to they're going to look like Xi naively rather than looking like 1 over Xi. So that means that the gradient descent update rule becomes extremely unstable when the scales of the individual features are very different. And so your convergence time can be atrociously slow. Right, so this is just saying what you said. So the update rule, so if we think of Xi as having units of I guess, then the units of Wi should have units of 1 over I. And that's just not what the update rule is doing. So you would like to have a way to normalize the features so that things work, but doing a direct normalization is actually kind of awkward. So there's this Gaussian sphering approach, where for every feature you compute the mean, and then you compute a standard deviation around the mean, and then you substitute the standard and standard deviation standardized features. So that's a reasonable approach, and that actually works pretty well, I think, when you can afford to do it. But you kind of lose your online structure to your solution, which is a bit painful. And then if you have a sparse data set, it blows things up enormously. Right? So for RCV1, it'd become a factor of 500 larger. So you'd be looking at a 500 gigabyte data file rather than a 1.1 gigabyte data file. Right? So that's kind of awkward.
Implicitly.
What's that?
Unless you do it implicitly.
Yeah. So I'm going to talk about a way to get at not fully doing this implicitly. So doing this implicitly with the Muse is actually kind of tricky because just subtraction is harder than division. But turns out you can do something for division-wise. This is a scale-free update rule. So we're going to have a scale and an overall normalizer. We're going to renormalize the Wi to a new scale whenever we discover that the feature value is too large. And then we're going to adjust the scale, just to remember what we're using. And then we're going to adjust our global scale. And then we're going to use that scale adjustment. Okay, so we're just about out of time.
It's something like very similar like gradient clipping.
Gradient clipping. I don't know gradient clipping.
Maybe you want to like normalize
like if a gradient is larger than a limit, then you just like reduce it to that limit.
This is not reducing the limit. This is rescaling things because we have that 1 over SI squared. So there's a 1 over SI squared and makes every unit be correct. The units in the I dimension are 1 over I. So the units of Wi are 1 over I, and the units of the update are like 1 over I. Okay, so if we go back here, the default update rule in VW uses all of these things together. And all those things together give you a loss of 5.1%. So this is essentially how we create a good, stable, online gradient descent type of learning algorithm, for linear learning at least. But I would emphasize that this is not really the end. There's quite a few more tricks needed for nonlinear systems. Adam, I think you mentioned, is another example. If you want to try to do second order learning, that's important at times. And so maybe we'll have another lecture sometime later discussing more advanced optimization techniques. Okay, are there any questions?
Just one more question.
Yeah.
So when you were doing binary classification as a simplest example, what's the really good way to handle class imbalance. Assuming you don't have any prior knowledge about training sample, but let's say you have highly imbalanced ratio of positive sample against negative sample. What's your usual treatment to handle this?
So I think it really depends on the setting quite a bit. There's settings like image classification where there's no real sense in which the training set reflects the distribution that you encounter in the real world. And then I think what you really want to be doing is you want to be kind of reweighting things so that every class has the same importance. And then you just work with that. But on the other hand, if it's truly the case in the real world that one class is just much rarer than the other class, and that's reflected in your training set appropriately, I don't think you want to reweight. Or if you do want to reweight, it's only very lightly. Because if your learning algorithm isn't truly optimizing the loss that it's supposed to be optimizing, it should be taking into account the relative rarity of one class over another in its propensity to predict that rare class.
Perfect.
All right, thank you. See you guys next week.
So with the subgradient thing, it's pretty simple. I was just thinking about it. It's so I was talking about